Have you ever heard of Hawking radiation, which can bring an end to even black holes, known as the deadliest and most inescapable things in the universe? In my previous videos, I only touched upon it briefly and hadn't discussed Hawking radiation in detail. Today, we will take a look at what Hawking radiation is, how it works, and how it was discovered. Before we get into our video, if you enjoy these types of videos, don't forget to subscribe to my channel, like my videos, and leave a comment to give ideas about both current and future videos. Now, if you are ready, let's go back to the years when Hawking radiation was first proposed. First of all, up until modern astrophysics, black holes were always seen as extremely mysterious, a cosmic prison that could pull in all kinds of matter, and even non-matter, from which absolutely nothing could escape. These structures were always considered the absolute extreme of classical physics by scientists and space enthusiasts. In fact, for a very long time, people thought black holes were the end of the universe. However, by the mid-20th century, an idea was put forward that fundamentally changed these thoughts and the unknown. This idea suggested that black holes might not actually be completely black. This concept, which confused everyone and created a true epiphany, would later be called Hawking radiation. When the calendar showed 1974, the English theoretical physicist Stephen Hawking proposed the idea of Hawking radiation for the first time. But to understand this idea, or rather this discovery, we need to go back a little further in time. In the early 20th century, Albert Einstein's theory of general relativity explained how gravity warps space-time. According to this theory, extremely massive objects bent space-time so strongly that, beyond a certain point, nothing could escape this flow, or rather, this gravitational pull. This boundary, as you all know, was called the event horizon. As you know, it is impossible for anything that crosses the event horizon to ever return. For a very long time, physicists accepted that black holes behaved this way. However, as time progressed and the 1970s arrived, scientists trying to build a bridge between quantum mechanics and general relativity began to realize that very different things could be happening around the event horizon. According to quantum mechanics, a vacuum is never completely empty. Virtual particles constantly appear and disappear in space. These particles usually emerge as a particle and its opposite, an antiparticle, and they annihilate each other, turning back into energy. Right at this point, our brilliant theoretical physicist Stephen Hawking stepped in and presented an extraordinary idea. If these virtual particle pairs formed near the event horizon of a black hole, one of these pairs could fall into the black hole while the other could escape. Under normal circumstances, while these particles would annihilate each other when they form near a black hole, this process is left incomplete. One goes inside and the other goes outside. The escaping particle would appear as a real particle to an outside observer. This exact event was the sole and primary reason that made the black hole appeared to be emitting radiation. This radiation was named Hawking radiation. This discovery sent shockwaves through the physics world because it showed that black holes were not completely black. More importantly, this process caused black holes to lose energy over time and eventually disappear completely. So quite shockingly, objects that were called immortal, indestructible, and that destroyed everything else, black holes, could actually fade away. One of the most striking consequences of Hawking radiation is that black holes have a temperature. From the perspective of classical physics, it seems impossible for a black hole to have a temperature because nothing can escape it. However, when quantum effects come into play, it turns out that black holes actually have a specific temperature and emit radiation depending on this temperature. Interestingly, the smaller the black hole, the hotter it is, meaning smaller black holes are more affected by radiation than large or supermassive black holes and evaporate much faster. This situation gives us crucial clues about the future of our universe. In the context of cosmic time, over extremely long timescales, long after stars have burned out and galaxies have dispersed, even the remaining black holes will eventually disappear due to Hawking radiation. This shows that in the infinite fate of the universe, no structure will exist forever. Hawking radiation also brought up the information paradox, one of the biggest problems in modern physics. The question of what happens to information that falls into a black hole has occupied physicists for years. Because according to quantum mechanics, information cannot be destroyed, yet black holes seem to destroy this information. If a black hole completely disappears due to Hawking radiation, the question arises of what happened to the information that fell into it. This problem remains entirely unsolved and continues to be one of the greatest mysteries of theoretical physics. I should also mention that when looking at its effects on space and the universe, Hawking radiation is not a directly observed phenomenon because this radiation is incredibly weak. Especially for large black holes, this radiation is almost immeasurably small. However, theoretically, small black holes in the universe especially primordial black holes that might have formed in the early universe, could explode and disappear thanks to this radiation. Such explosions could manifest as high-energy gamma rays, and scientists are trying to observe Hawking radiation indirectly by searching for such signals. Another important aspect of Hawking radiation is that it is one of the rare points where general relativity and quantum mechanics merge. This theory is one of the cornerstones of quantum gravity studies, which attempts to address two major physics theories within the same framework. Therefore, Hawking radiation is not just a discovery about black holes, but also a massive step towards understanding the most fundamental laws of the universe. Moreover, the evaporation of black holes is an incredibly slow process. For instance, the lifespan of a star can last for billions of years, and galaxies can continue to exist for trillions of years. However, the time required for black holes to completely disappear is far beyond even these durations. For example, the time required for a black hole with the mass of our Sun to evaporate is millions of times longer than the 13.8 billion year age of the universe. I want to emphasize this specifically, millions of times. Now imagine much more massive black holes. As the mass increases, this required time increases exponentially, which leads to this thought: even if it is known for certain that black holes can disappear or evaporate, the time required for this to happen is incredibly long. I don't think any life system capable of witnessing this time frame, or even the universe itself, could survive until those periods. This is exactly one of the main reasons why Hawking radiation cannot be observed directly and in the short term, as I mentioned earlier. Massive black holes lose energy so slowly that this process seems almost static in the current age of the universe. But according to theory, this process never ever stops. Even though the black hole is incredibly slow, it constantly loses energy, and as its mass decreases, its temperature increases. This means a dramatic acceleration towards the end of the evaporation process. In the final stage, the black hole can disappear in a massive burst of energy in a very short time. This explosion could be one of the observable high-energy events in the universe. I keep saying could or might, because due to the colossal time frames I just mentioned, we haven't witnessed a black hole explosion so far, and we highly likely never will. One of the strangest things is, if a particle is escaping from a black hole, where does this energy come from? Actually, at this point, Hawking's answer is quite bizarre, but it is something plausible according to quantum mechanics. According to Hawking's idea, or rather his solution, the particle falling into the black hole can possess negative energy. That is, when a particle carrying negative energy falls into the black hole, the total energy of the black hole decreases. This causes the mass of the black hole to shrink. The escaping particle, on the other hand, carries positive energy and becomes observable. It is this process that leads to the slow melting away of the black hole. When we think about the effects of Hawking radiation on the universe, we can say that this effect is at a very limited level in today's universe. However, over extremely long timescales, this effect becomes quite dominant, especially in the heat death scenario regarding the future of the universe. After stars fade and new star formation stops, the most important structures remaining will be black holes. But thanks to Hawking radiation, they too will disappear, leaving nothing but low-energy particles in the universe. This points to an ending where the universe becomes completely dark and cold. At the same time, this theory brings along philosophical questions regarding the nature of physical reality. If even black holes are not eternal, is there really nothing permanent in this vast universe we live in? The information paradox, in particular, is one of the most controversial aspects of this topic. What happens to the information carried by a book, a star, or any physical system that falls into a black hole? If the black hole completely evaporates, is this information destroyed? Quantum mechanics states that information cannot be destroyed, but the classical understanding of black holes implies that the information cannot be retrieved. Initially, Hawking radiation did not seem to carry this information, which created a massive contradiction within the subject. However, over the years, many theories have been developed by various groups regarding this problem. Some physicists argued that the information returns through Hawking radiation in a highly complex and scattered manner. Others suggested that the information is stored at the event horizon, forming some kind of holographic structure. These ideas have become one of the most active fields of research in modern theoretical physics. Furthermore, some people argue that because Hawking radiation cannot be observed directly, there is no such thing, or that everything we know about this subject could be wrong. However, this is entirely related to our technological limits and boundaries of knowledge. Current telescopes and detectors do not have the sensitivity to pick up such a weak signal. But scientists are trying to test this phenomenon through indirect ways. For example, similar effects have been observed on analog black holes created in laboratory environments. These experiments support the idea that the fundamental principles of Hawking radiation might be correct. And there you have it, my dear friends. This is how we can briefly summarize Hawking radiation. Thanks to Hawking radiation, we now know very well that everything in the universe has an end, and that even massive black holes cannot live forever. The fact that we still haven't found or fully understood much about Hawking radiation, despite the decades that have passed, makes it even more fascinating and mysterious. Have no doubt that the moment there is the slightest development, I will prepare a detailed video about it again and share it with you. I hope you enjoyed my video. If you did, don't forget to hit the like button below, subscribe to my channel to support me, and leave a comment for new video ideas. Until we meet in our next video, take great care of yourselves. Goodbye.